Using this and using what we worked out for the potential energy, we found that we could generalize this and say that a relationship between the change in electric potential and the electric field is the negative Ex delta x plus Ey delta y, if we had motion in more than one dimension here, plus Ez times delta z, or more compactly, we can say it's negative of the electric field dot product with delta L. Okay, I should say that this is for the case of a constant or a uniform electric field, but we'll deal just with uniform fields for right now. And the important thing to realize here is we're always looking at, it's a scalar. It's giving us a scalar. Like any dot product, it's giving us just a single number. It can be positive or negative, but it's not a vector quantity. We're combining two vector quantities, and those quantities are the field, the electric field, and the path. So delta L is a path vector. So when we're calculating a potential difference, you always want to keep in mind, what is the path? What direction are we moving along a path? And what's the field? What's the electric field along that path? Okay. The path could just be any generic path. It doesn't necessarily have to be a path that a charge is actually moving, because again, we're sort of dividing out the charge dependence and looking at something more general. But there's always a path there that if we had a charge moving along that path, we could then figure out what the change in potential energy would be for that situation. Okay. So this is best the best way to get used to this is to just try some examples.